right? Only when theta 2 is equal to 0, this will be a singular posture. So this configuration will be like this. This is theta 2 is 0 here. Okay, this is a singular posture. Now, at what angle the determinant will be maximum? Plus or minus 90 degrees, because it's a determinant, we'll only take the positive value. So at theta 2, equal to plus or minus 90 degrees, this will be maximum. So the determinant of the Jacobian will be maximum. So any configuration that is like this will have maximum. In this case, you can easily generate motion in any direction. This is theta 2 is equals to 90. This is theta 1. Theta 1 is, it does not depend on theta 1, it only depends on theta 2. Okay, this is maximum. This is full rank. You can generate motion in any given direction. So, in this case, you can easily derive, because it's only a function of two angles, theta 1 and theta 2, you can derive this. But if I give you a 6 degree of freedom manipulator and I ask you to find all singular positions, it's really difficult, because when you multiply 6 thetas, the forward kinematic equations are immensely long, and that's why we did what we did when we studied decoupling. So we'll apply the same concept of decoupling in this case. So we'll say that if you have a Jacobian for a 6 degree of freedom manipulator, 3 joints go to positioning, 3 degrees of freedom are for positioning, and 3 degrees of freedom are for orientation. Okay, 3 degrees are for positioning and 3 degrees are for orientation. So I can write the Jacobian J like this, right? J1, J2, J3, J4, J5, and J6. Okay, these are my positioning joints. These are my orientation joints. Okay, so I can write this matrix like this: JP, right, and JO. Alright, JP and JO. JP is for the Jacobian of the positioning part. This is Jacobian of the orientation part. Now, we know that every Jacobian is like this. Every Jacobian column is like this. It has V and omega. Right? So I'll write this as J11, J12, I'm sorry. Okay, that means I'll split this like this, because it has a velocity component. The top 3 is a velocity component, the bottom 3 is this is linear velocity and angular velocity components. 2 components of the Jacobian for every column, so I can write this as this. So what will be the order of this matrix? All the 4 matrices, what will be the order? What will be the dimensions of these matrices?
6 by 6.
The whole thing is 6 by 6. This is 6 by 6. What will be the order of these 4?
3 plus 2.
Huh? What will be the order of this?
3 by 3.
3 by 3, because there are 3 columns. Each one of them will have 3 rows, right? Because Vx, Vy, Vz, phi, theta, and psi. Okay? So each one of these, J1, J12, J21, J22, they'll all belong to matrix 3 by 3. Okay, they are 3 by 3 matrices. All right. So now that we have decoupled them, let's look at this part. Okay, this part is fine. Let's look at this. Let's say that this is a spherical wrist. Okay, if the last 3 joints are or constitute a spherical wrist, okay, if the last 3 joints constitute a spherical wrist, then JO will be equal to last 3 joints, N is equals to 4, 5, and 6, right? Or we'll call it as I. Let me use the number I. I goes from 1 to 6. Now if you remember, what is the Jacobian of a revolute joint is as follows. Zi minus 1 cross On minus OI minus 1, and here, right? So in this case, we'll have this as J4 this will be Zi minus 1. So in this case, this will be Z3 cross O6 minus O3. And this is Z3. Z4. So, 4. Because it's a spherical wrist, all these origins coincide. This will be 0. If you look at the Jacobian that we did in class, you will see last time that the third column has the top row is all zeros, right? Because the wrists are all because it's a spherical wrist, O4, O3, O4, O5, O6, they are at the same point. So this will all lead to a 0 matrix. So this will be equal to 0, Z3, 0, Z4, 0, Z5, right? But we also know that JO is equal to this. JO is equals to 0, Z3, 0, Z4, and 0, Z5. This is equal to J12 and J22. Let me write it here again. I'll write it once more so you can see that. So let me write it here once again. So this is 0, 0, 0, Z3, Z4, and Z5. This is equal to J12 and J22. From here you can say that J12 is 0. The top part, which is J12 is 0. If J12 becomes 0, JO is nothing but 0, J22. Okay, this is this. Okay, so if JO is 0, 2, 2, then the Jacobian here, which is equal to J, which is equal to JP, and JO will be equal to J11, J21, 0, J2. Okay, so the determinant of the Jacobian, determinant of this, will be equal to We did, whenever, as I mentioned to you, if you have a matrix like this, if you have A, which is A, B, C, D, then the determinant of A is AD minus BC, right? So in this case, these are matrices. So AD, this is A, D, B is 0, and C is this. So when I multiply this and this will become 0. The only thing will be determinant of J1 times determinant of J2. Alright, so when you multiply the two determinants, we can get this. So we can find singular postures by doing this. When the product is equal to 0, so if determinant of J is equal to 0, we want to check singularities. That means this can be 0 because it's a product. Either this can be 0 or this can be 0. So to check for singularities, check these two conditions. First condition, determinant of J11 equal to 0. Second condition, check when determinant of J22 is equal to 0. So this reduces to determining the Jacobian of, or finding for only matrices of the 3 by 3 order. Otherwise, you would have ended up checking for a determinant of a J6 by 6, which is very difficult to do because you'll have 6 tetras. In this case, you're limiting it to only a 3 by 3 matrix. So if you check these two, you should be fine. This will give you isolating wrist. This will give you positioning singularities. This will be arm singularities. And this will be wrist singularities. Okay, so you can decouple singularities like this. Once you set up a Jacobian, you can only take the top part, find when this is equal to 0, and this. Once you take the union of the two, that will be the list of all the singular postures. This will give you arm singularities, this will give you all the wrist singularities. Okay. So let's just recap the properties of a singular position. What happens at a singular position? So properties of a singular position or singularity. Okay. First one is that the rank of G of Q, all right, is less than full rank, or less than minimum of n or 6. One of the two. Second, which is the necessary and essential condition, which is determinant of J of Q is equals to 0. Okay, and the third one is at a singularity, motion in one or more directions is not possible. Okay, or we can say that at singular postures, bounded end effector motion requires infinite forces or torques. What do you mean by bounded end effector motion? What does this mean? What does bounded end effector motion mean? Bounded means finite. That means if I want to move, let's say I'm at one particular posture, like this with my arm, I want to move in this direction at 1 meter per second or something, right? That's bounded. That means you quantify it. Bounded end effector motion requires infinite forces. That means even though you know that you want to generate a small amount of motion, exactly how much you need in a particular direction, it is impossible because it will require, in other words, you can say bounded end effector motion requires unbounded forces or torques. That means even though I apply an infinite force, I cannot move in this direction. Same thing with the orientation. When θ2, the second joint is 90, no matter how much you turn it, you will not turn in that direction, you will turn in other directions. And finally, you can say that incremental motion which can be something as delta Vx or delta theta dot x or y or whatever. That means velocity, change in velocity, or let's call it as delta x only position. How about unit time will give you velocity. It is impossible in certain directions. So, in some directions, even moving a small perturbation or a small incremental motion is impossible. So this is pretty much the properties of a Jacobian. But if you look at this, there is one big problem that we have not seen yet, which is if the Jacobian is square, that means if the Jacobian is a square matrix, right, which is 2 by 2 or something like that, you can calculate the determinant because the determinant exists for square matrix. What happens when the when the Jacobian is a non-square matrix? So the Jacobian will have, you know that it will have 6 rows. Let's say you have a Scaraf manipulator, right? N is equals to 4. The dimensions of the Jacobian will be 6 rows and 4 columns. You cannot calculate the determinant of a non-square matrix. If a matrix is non-square, you cannot compute the determinant. So what do? So in this case, when you cannot compute like this. This will not help. So in this case, the determinant of a Jacobian will be equal to square root of the determinant of J times J transpose. This is for a non-square Jacobian. Okay, we'll have to take the square root of the determinant and its transpose. So we'll do an example of singularity decoupling because I'm going to give you a analytical question to find the Jacobian. Once we find what is the analytical expression which you will derive, then we can take it forward to find singularities. Once you find the Jacobian, we can find the singularities from the Jacobian. So I'm going to do an example in the coming class where we can decompose the singularities. Let's talk about acceleration, manipulator acceleration. And it has its own challenges. So we know that x or eta is equals to jq times q dot, right? This is the end effector velocity. This is your joint velocity. Now if I want to find acceleration, which is eta dot, I'll have to differentiate this with time. So dt of eta will be equal to So eta dot, which is your acceleration, right? This is your end effector acceleration. Will be equal to, the determinant will write this as J of Q times Q dot, right? Plus this is your joint acceleration. Okay, so in this case, you can find what will be the end effector acceleration given the joint acceleration. So from here, you can find end effector acceleration. Which is eta dot given Q dot and Q double dot. Right? We need Q to compute J of Q, you need Q dot to compute the spot, and you need Q double dot. So all three must be given, and then you can find what is the end effector acceleration. Now you can have the inverse problem where find, just like we did forward and inverse with velocity and position, we can do the inverse acceleration. Which is basically find Q double dot. You need to find Q double dot. So we'll use this equation. So we know that eta dot, or the acceleration, is equal to J of Q times Q double dot plus d of dt of the Jacobian times Q dot. Right? Now if I want to find this, then I'll have J of Q dot will be equal to eta dot minus d of dt So I want to get rid of J of Q, so what I'll do is I'll multiply by the inverse of J of Q. So you can generate, this will give you the joint accelerations needed for a given joint acceleration, end effector acceleration. So here you need to know, find Q double dot given eta dot Q, and I'm sorry, you cannot have Q double dot. Okay. These are simple matrices. Obviously, you don't do this by hand. Most of this is programmed so that you can compute the accelerations and everything. The only problem is here, and I'll talk about this in details. Again, computing the inverse is not possible. When the rank drops below full rank, this will be 0. You won't get an inverse. So we do what is called a pseudo inverse. We'll talk about it in the coming class. I think we have a few minutes. I want to give you your in-class exam papers, okay? And if you go over that, can you give them the papers? If you have any questions, let me know. The take-home part, I'll give it to you in the next class, okay? I just make sure that, we finish within the class time because I don't want a crowd here. There is another class after this right away. So I would have loved to give you this at the end of the course, but we will all block up the space. If you have any questions with this or the paper, just stop by.